So Broca and Vernicas formulated their hypotheses about language in the brain about 150 years ago, resulting in what we call the classic model still today. But what do we think about these hypotheses today? Which parts of the model have survived to modern times, and which parts do we not really believe so much anymore? First, before we start discussing that, it's important to notice that even if every bit of the classic model was completely correct, it would still be an incomplete model of the neurobiology of language. And the reason for that is that the classic model only really talked about the processing and the production of individual words. It did not really talk about how we put words together into larger expressions. But that really is the essence of language. Language is not just strings of isolated words. The reason language is such a powerful device for expressing our thoughts and communicating is because we're able to combine smaller pieces of meaning into larger expressions. So ultimately, our models and theories about the neural basis of language will need to say a lot about this capacity to compose complex meanings with language. But then the classic model just didn't get to that part yet. Okay, so let's look at the parts of the classic model and sort of go through them, considering what the longevity of these components of the model has been. The brief summary would be that the hypothesis that something like Vernicas area represents the sounds of words is probably the part that has had the most longevity. So we still think that posterior temporal cortex is very important for phonological access. And the most controversial part of the model then is Broca's area. So there has been tremendous debate about exactly what the functional contribution of Broca's area is to language. The other two parts are a little less crucial to the classic model, but certainly we still believe and know that Broca's and Vernicas areas are connected by the arcuofasciculus and that there are specific aphasias that correlate with impairment in that area. And then this idea that our semantic representations, so the representations of the meanings of the words, are kind of all over the place in the brain, so they're neurally distributed. That is definitely something that we still believe. The debate has more to do with whether, in addition to these distributed representations, we also have localized, more focal representations somewhere in the brain. So that's more the nature of the debate about semantic representations. So now let's talk a little bit more about Vernicas and Broca's areas more specifically and what we think about these regions today. Okay, so Vernicas area. So what do we think about Vernicas area today? Here's an influential model by David Puppel and Greg Hickok that clearly shows that Vernicas area and the idea that this posterior temporal cortex houses some type of phonological representations is quite well represented here. So the relevant area is the yellow blob, which they call the phonological network. And here you see that area then connects to what they call a lexical interface. So this in fact represents a hypothesis in which the meanings of words in fact sort of have a location in the brain, so not just a distributed model. But the phonological network is localized very much around the Vernicas area. Here's another slightly more recent model, the encoding of speech sounds in the superior temporal gyrus. So that already sounds very much like Vernicas' hypothesis. Speech sounds are encoded in superior temporal cortex. So let's look at some specific bits from this. So they say the human superior temporal gyrus is critical for extracting meaningful linguistic features uniform speech input. So that's basically what Vernicas said. Local neural populations are tuned to acoustic phonetic features of all consonants and vowels and to dynamic cues for intonational pitch. So what that's conveying is our more detailed understanding of the representations that actually live in superior temporal cortex. So we today have evidence that in fact all categories of speech sounds in a person's language kind of occupy their own bits of cortex in this area. And then the major questions in today's research are questions such as what's expressed here. So currently a major challenge is to understand how these features are integrated across space and time in the brain during natural speech comprehension. So what seems to be clear still today is that posterior superior temporal cortex does represent speech sounds. What's less clear, and this is kind of interesting, is where Vernicas area actually is. So, for example, if you go to image Google and just enter Vernicas area, you get all sorts of different localizations of this area. So here, for example, in Britannica.com, you see that Vernicas area occupies this huge amount of area. So it, has temporal cortex, but then it extends way into parietal cortex, which is very different from the other Vernicas area blobs in these other pictures. So just other Google image hits for Vernicas area. So here, it's rather more inferior to these other two. So you see that there's a decent amount of variability. And so with respect to this, I don't have anything more insightful to say, except that maybe just not use the term Vernicas area when you're trying to describe a specific brain area. It's kind of confusing and we don't really have a good agreement of exactly what Vernicas area means. So it's more a historical term. Okay, what about Broca's area then? Well, interestingly, the situation with Broca's area is sort of the reverse from Vernicas area. So, first of all, we don't really fight about where Broca's area is. If you Google Broca's area, you pretty much get the localization that it is Brodmann areas 44 and 45. Shown here, so that's just from Wikipedia. So these are the two Brodmann areas. That's pretty much where we think Broca's area is. Sometimes you'll see area 47 included in Broca's area, so that would be right below these two areas, but that's a little bit rarer. However, as I already alluded to before, what is not clear is what Broca's area actually does. So that has created a lot of controversy. So obviously we have the original hypothesis from Paul Broca that it participates in production or is crucial for language production, but Broca's area also figures in almost every other aspect of language processing. So you'll find hypotheses that attribute Broca's area to aspects of lexical access, activating your word representations, syntax, morphology, you name it, Broca's area really is kind of all over the place and probably has been the most debated area in language research. And the debate very much started with the observations of two aphasiologists in the early 80s, Goodglass and Kaplan, who noticed that Broca's aphasia, despite Broca's original description, really isn't just a production problem. So Paul Broca described his patients as having this, really laborious production, but these researchers noticed that actually Broca's aphasics also don't comprehend language totally normally. And so their original formulation of the issue was something like, Broca's aphasics may be confused by more complex spoken messages. So what does that then mean more specifically? Well, in particular, these patients were reported to make a lot of mistakes with expressions where the so-called canonical order of the person who's doing the action, so we call that event participant, the agent, and the thing that's acted upon, technical term patient, is reversed. So here we have an active sentence in English: the girl chased the boy. Okay, so here the girl is the actor and the boy is the acted upon participant. And in English, we would usually expect to see the actor in the first subject position and then the boy in the post-verbal object position. But this order can be reversed by various tricks that the syntax can play on the expression. And so, for example, here we have the passive version of that sentence, where now instead of the actor, we get the acted upon participant first, the patient. The boy was chased by the girl. So here you really have to use syntactic knowledge about the language in order to get the meaning right. So now it's not the boy is not the chaser, it's still the girl that's the chaser. And so these kinds of expressions seem to be tricky for Broca's aphasics, and that gave birth to a very, very large literature trying to figure out exactly what's going on here. And then this sort of suggested that maybe there's something about syntactic processing that is difficult in the comprehension of Broca's aphasics. And then that type of hypothesis was further bolstered by an early neuroimaging study by Karen Stromsvold and colleagues, who did a manipulation where you had exactly a condition where there was kind of like easy syntax, so an easy sentential structure, versus a structure that was much harder to process. And now you're just measuring completely healthy research participants. And what they noticed was that Broca's area actually lit up, was activated more by the more difficult syntax than the easy syntax. So this kind of collection of findings gave birth to a very prominent hypothesis that Broca's area is the syntax region of the brain. And again, if you ask Google today, where is syntax in the brain, Google will actually tell you that it is in Broca's area. At least today in 2020, that was still the case when I checked this morning. But in this course, we'll talk about challenges to this hypothesis. It turns out to be problematic in various ways, but it's definitely been a prominent hypothesis. What about then the articulatory production side of the hypothesis about the contribution of Broca's area? We'll talk about this more later on in the course, but here is a little piece from a paper from 2015, so 5 years ago, that tells us a little bit about how our understanding has evolved. So here, what these authors say is that, so first they review, so Broca's area is widely recognized to be important for speech production. So that was the Broca's original hypothesis, but its specific role in the dynamics of cortical language networks remains unknown. And so here what they report is that Broca's area mediates a cascade of activation from sensory representations of words, so those are the sound representations of words, in temporal cortex, so that would be Vernicas area, to their corresponding articulatory gestures in motor cortex. But it is surprisingly quiescent during articulation. So when you're actually talking, it doesn't seem that there's a lot of signal in Broca's area. So contrary to classic notions of this area, of this area's role in speech, our results indicate that Broca's area does not participate in production of individual words, but coordinates the transformation of information processing across large-scale cortical networks involved in spoken word production prior to articulation. So this kind of transformation, as opposed to really like orchestrating the articulation itself. So my summary of Broca's area, the role of Broca's area for now, is simply that it's still controversial, still very much a topic of active research. Today, we also know that the correlation between damage in Broca's area, so when you sort of take out Broca's area from the picture, and the behavioral pattern of Broca's aphasia is actually much, much weaker than what we originally might have thought on the basis of Broca's findings. So it turns out that having damage in Broca's area really does not necessarily cause Broca's aphasia, and having Broca's aphasia does not necessarily mean that you have damage in Broca's area. And in order for that to make any sense, you need to know a little bit about how aphasia is diagnosed. So diagnosis of aphasia is always done on the basis of a behavioral battery. So it's not the case that you image the brain. So even in modern times, it's not the case you image the brain. It's like, oh, you have damage in Broca's area, therefore you have Broca's aphasia. Rather, you need to show the characteristic behavior of a Broca's aphasic in order to be diagnosed as such. So always done on the basis of performance on a battery of language tests. And so here's a couple commonly used ones, like the Boston Diagnostic Aphasia Examination or the Western Aphasia Battery. And so the lesion site, in fact, does not play into the diagnosis. So it doesn't matter where the brain damage is, your diagnosis as Broca's aphasics, Vernicas aphasics, or other types of aphasics that we'll learn about later, does not, where the damage is does not play into that diagnosis. So it's possible to have Broca's aphasia without having damage to Broca's area. Similarly, Vernicas aphasia without damage to Vernicas area. And a scientist called Nina Dronkers has characterized this relationship between aphasias and specific lesion sites really beautifully. So we'll look at her work a little bit here. So here specifically about the relationship between Broca's area and Broca's aphasia. So first of all, only 50 to 60% of patients with lesions in Broca's area have persisting Broca's aphasia. So let's imagine that these are all our people who have a lesion in Broca's area. So here's Broca's original brain tan. And so then only about half of those would then also show the behavioral profile of Broca's aphasia. So it's kind of like really laborious production. So that's a very, very weak association. How about then if we look at the people, so here's 100 people who all have the behavioral profile of Broca's aphasia, so these people have all been diagnosed as Broca's aphasics, how many of them would have damage in Broca's area? And so here it's a little bit better, so something like 85% of patients with Broca's aphasia then also have damage in Broca's area. So not at all, a full relationships where having damage in Broca's area means that you're Broca's aphasic or vice versa. And something really interesting also turns out to be the case when we consider the original patient of Broca, so-called Tan, and his damage. So Broca did not choose to dissect his brain post-mortem because he wanted to preserve that brain. And I already showed you a picture of the brain in a museum of Paris. So that brain has been preserved. And so the consequence of that is that we've only ever been able to, or what Broca was able to see was just the surface of the brain. Just the damage that's very apparent on the outside. But there's of course a lot of brain that you're not able to visualize that way. And so the question is, what does that brain look like if we were to image it with modern neuroimaging? And Nina Dronkers had the opportunity to do that. So she did high resolution MRI, so we'll talk about these techniques next time, to actually figure out the extent of the damage in this original brain. So this is just the lateral view of the brain. So you see the lesion here. It's a close-up, but other than that, the brain looks pretty good. However, what the MRI imaging revealed is that actually in this original brain that really gave birth to the hypothesis that Broca's area participates in speech production, the damage was much more significant. So first of all, the left hemisphere was clearly smaller than the right hemisphere due to the destruction of cortex and white matter throughout the hemisphere. And then the lesion sites were many. So obviously left inferior frontal cortex or frontal gyrus, so that's Broca's area. Also deep inferior parietal lobe, anterior superior temporal cortex, so that's, you know, kind of all the lobes. Extensive subcortical involvement, lots of different subcortical structures. A structure called insula, so that's kind of like tucked underneath Broca's area, so that was completely destroyed. The entire superior longitudinal fasciculus, along with other frontal parietal white matter, and so forth. So the bottom line is that lots of structures were damaged, but crucially, they were all left hemisphere structures, so the right hemisphere was unaffected. And so now the really interesting conclusion from this is that if Paul Broca had actually had access to modern brain imaging of the sort that Nina Dronkers had access to, his conclusions about the brain organization of language would have probably been very different. And then also, obviously, consequently, Vernicas and Lichtheim's, because they sort of put it all together. And so it's quite possible that this very simple classic model of language in the brain might have never existed. We might have had something much more complicated from the get-go. Nevertheless, the classic model has functioned as a very good working hypothesis for researchers, probably because of its simplicity. So it's something that is much easier to falsify, given that it's relatively simple. Just a short note about aphasia recovery, since it's also important to understand when we make sort of functional conclusions from the behavioral profiles of aphasic patients about specific brain regions. So during the first 3 months after the incident that has caused the brain damage, so let's just say stroke, there can be a lot of reorganization in the brain. There can even be complete spontaneous recovery. So having brain damage does not mean that you will have long-lasting problems. Rather, you probably have some problems at the beginning, but a lot of it may subside. And typically, the subjects that you'll see in aphasia studies are not recent stroke victims. So it's not the case that they've just had the damage has just occurred and we're now sort of studying the consequences of that very fresh, but rather patients whose situations have really stabilized. So they probably have had a lot of that reorganization happen. And crucially, that reorganization most likely looks different for each individual. And so there's a lot of variability in the extent to which the recovery happens and also how it happens. And this is something that we need to keep in mind, since it does complicate our ability to use aphasiology to inform specific brain functions. There's just tremendous variability in the patient population. And so that's it for aphasia for now. Next, we'll talk about our modern techniques to measure brain activity in the awake behaving human. I'll see you then.